Dear everybody, excuse for this special introduction, but we lost the sound of Chef van der Steen in the beginning of his talk. This is a very nice talk and the most recent update on the Insignia results that Chef van der Steen did present at the BeeHealth symposium in Madrid in June this year, and it's really worthwhile listening to and see it. I'm sitting in the audience. I gave him a microphone and I recorded his talk and I tried to zoom in and out on the slides as good as I could. Therefore, the quality, it was dark in the room, but I think it's worthwhile listening to the talk. And what you don't get the first minutes is that Sjef, he says, welcome to everybody. He's very happy to be invited and telling about this unique project that we have been doing over the last years using honeybees to monitor pollutants in our environment. And even as exciting was that we're using beekeepers as citizen scientists. So in all the European Union countries, we had more than 315 apiaries collecting samples 9 times during the season from April until August. Please let me hand over to Chef and his sound. Enjoy this talk.
And along with collecting this food, they take all kind of contaminants. So the bees do the work. And then it's up to the people, and in this case, the citizen scientists, and I'll come back to that, to sample the honeybee colonies. And sampling honeybee colonies sounds quite easy. Just take some bees or honey or pollen. But we didn't want to do that because when you take samples, you have to kill your bees. That's first we want to prevent. So we decided to develop in-hive passive samplers, and we succeeded to invent this kind of samplers. So we invited the apistrip, which is a passive sampler, to collect all the pesticides that bees are bringing in. We made an apitrap, which is a passive sampler for microplastics, and in between, I warn you, we do have a lot of microplastics and we do have a lot of pesticides. We collected little piece of honey. We used silicon bands, the simple bands that you use when you go to the hospital or to a festival. They are excellent passive samplers for air pollutants. And we collected propolis. And we did it, as I told you, in all the European countries, so all the 27 European countries, together with 315 apiaries. And imagine you want to make a pan-European study without citizen scientists. It's impossible. You need all those beekeepers. And the beekeepers are very welcome and are really willing to help bee science. So in these 27 countries, we had our contact persons, our national coordinators, who invited the beekeepers to participate. And not all beekeepers, because we did have many more beekeepers that wanted to participate, but we did our selection of the beekeepers based on the land use. We want to have this information on the different types. So we had bee colonies of apiaries, in this case, in agriculture areas, in urban areas, and in artificial areas. Artificial areas sounds a bit strange, but these are the cities and the forest. We have 9 sampling routes, all through the European Union, and it was every time on exact the same weekend. So we did our data all through Europe, from Norway, from Sweden up till Greece, to have this information all on the exact day, same time, and in the same methods, same time. So this makes it very, very valuable data which we can compare. So this is what we did in April till August. And now I show you some results, and I show you first the pesticides in the apistrip. Apistrip, you can see there on the right there. It's a very simple plastic plate, and we covered it with Tenax. Tenax is a polymer which is excellent for collecting all kinds of materials. We did it this time for pesticides, but we also did some studies for all kinds of new stuff like pheromones, etc. You all can collect it in this api strip. It's simple. You put it in the hive. Bees don't touch it. And we do it in the brood nest because there we have our favorite conditions of a very constant humidity and temperature, which is okay for our chemical physical reactions. And we left it there for 2 weeks. After 2 weeks, we changed it, and we collected altogether over almost 6,000 api strips. At the end, we had a recovery of 97.4%, so which is very good. Let me show you pesticides. There is not a region in Europe, in the European Union, where we had our apiaries where were no pesticides. So pesticides are everywhere, always. So they're ubiquitous in our environment. We have to deal with it. In our study, in which we analyzed 450 residues of pesticides, we detected over 200 pesticides collected by our bees. And the number of detections, you can see it there, it's 919. There were some apiaries in which we didn't find any pesticide, but it was only in periods of 2 weeks. The next 2 weeks we did find, so they are always, and maybe it's kind of coincident that we didn't find it. Anyway, it's only in 1.6% that we did not find pesticides. And we do have a top 4. It sounds a bit cynical to have a top 4 of pesticides, but these pesticides, azoxystrobin, boscalid, acetamiprid, and fluoriam, they are everywhere, always. And, Fanny already told something about it, we also have a lot of pesticides that are not anymore legislated. And I'll show you here. Here we have, how do I see? No. On the left hand, you have our dots, and this shows where we have our medium concentration. Every dot, there are 315 dots, are apiaries, and the blue dots have the medium number, which is very low. I must show you it is very low, which the bees bring in. That doesn't tell me what's on the bee, but this is what the bees bring in. And we did find on our api strips, and the blue dots are the average. We have yellow dots, which has the average plus the 2 times the standard deviation, and we have the red dots with 4 times the standard deviation. So I don't see, maybe you see it better, but there are several red dots all through Europe, which means that on these occasions you do have a significant amount of pesticides collected by the bees. There below we have the number of the average number of pesticides that we have. So we have on average 47 pesticides as a medium per apiary. So that is a lot. On the right hand, you have this box whisker graph, which shows you what's the average of pesticides that you find in the 2 weeks sampling based on the land use. And we do have about 4 in the agriculture areas and 2 in the cities and in nature. Cities and nature seems to be the same, and maybe you expect that in the forest and in the nature the air is clean and everything is clean. Forget it. It's not. There are pesticides everywhere, and maybe even more, and in this case the same as the cities, because pesticides, most of the pesticides are spread via the air. They are airborne, coming over the natural areas with a lot of forest, etc. It's colder there, the wind's going down, and there's this contamination. So that's why we have our pesticides also in the natural reservations. On the right hand, we do have, just to show you the number of DDT and its metabolites. You know, DDT, and I can see many of you are younger than 50, but in the old days we had DDT. It was very effective and we spread it everywhere. And about 60 years ago, they decided, oh, it is dangerous. It accumulates in the food chain and it gives a lot of very negative results. So about 60 years ago, it was decided to stop it. It's still produced but then exported, but that's another story. We stopped it by applying here in Europe. But still, after 60 years, we do find this DDT. And it's not that it's really spread again, but it's in the soil. Our soil, which we share with all the animals, is contaminated with DDT, and you still find it. So this is just a warning. I did put some names of countries behind it, but it's in all countries. Moving to the next slide, we had also checked our honey. Not for all pesticides, because most pesticides, and about 95 to 97%, we can find in the api-strips, but there are some pesticides, the very polar pesticides, we dissolve in water. And you find in honey, you can find in honey. And there was this very particular question, how do you, especially this glyphosate, the stuff to kill the green, is that in honey? And indeed, about 7% of all the honeys contained this kind of substances. In this case, the most of them was glyphosate and AMPA. AMPA is a residue of glyphosate, so it's this, you can put it together and then you see that about 80% of the honeys of this 7% has this glyphosate and its metabolites. And about 11% doesn't have it. So that's what we did find, and it's in line with the other results that were made on this field. We also tested the VOCs and the pHs. VOCs and pHs are volatile organic compounds and polycyclic aromatic carbohydrates. As I told you, we did it with silicon beds. You can buy it everywhere. Of course, you have to prepare them, you have to clean them very well, but then they are completely empty and they dissolve all kind of this kind of air pollutants. And there are many, many air pollutants. We selected these VOCs and pH based on their toxicity for mankind. And we did find them all. Some more, some less. For instance, for the VOCs, we did find a lot of hexane and benzene, octane, and also for the pHs, we had our naphthalanes, etc. So we do have our, could detect all these environmental pollutions. But most important is that with this method and our network of honeybee colonies that act as our biomonitoring tools, we do see when there's a point emissions, when there's suddenly a high increase, and that's important. So, bring to the microplastics. Microplastics are everywhere. That's not new, of course, we know that, we can read it every day in our papers, and we wanted to see, can we show them in our honeybee colonies, and that's why we developed the api-trap, which is on the right side for you. You see there's a sticky board, which we included in a frame, and also put it in the near brood nest with very constant conditions, and there's a constant airflow in the honeybee colony. Actually, the honeybee colony is breeding. Not really breeding, but it's kind of breeding. There's an air movement constantly. Bees are pushing out air and letting in air for the oxygen, and for the temperature regulation, and because of the temperature deviations inside the colony, because it's warmer in the brood nest than outside the brood nest, there's also constant air movement. And every square meter of air that we are breathing contains microplastics. So also what the colony is breathing contains microplastics. And we did find a lot of microplastics, actually altogether about 60,000 we could find on those AP traps. And on the left side you see a kind of examples. We split it up in films, fragments and fibers, and most of them were fibers. We also excluded all the natural fibers, so this is all synthetic plastics, and we could identify them morphologically but also chemically. And we do, you can see on the right hand how we did it, and most of them are polyesters and polypropylene and polyacrylonite, which are complicated names, but they are still all kind of polymers and plastics we have in our honeybee colony, we have in our environment. Brings me to the next metals. I don't have all the results yet, but we tested for about how many? 2, 4, 6, 8, 11 metals, and we do find them everywhere. But that's not that strange because we have our natural background. Our soils contains these kind of metals. So that's, we do find them, and we detected most of them, the magnesium, the chrome, nickel, and the lead. But most important, we could also see them as an indicator of point emissions, where there's suddenly a high increase of heavy metals, which is not normal and which can pose a risk for the health. We can see that very, very quickly. I show you some results of Spain, and you see on the right side that there's changing. And this changing with, and you can see it on top with the sampling rounds. So we had our sampling rounds and our bee codes. And in this case, you see the bee codes, Spain, then it's 20, then it starts at 1 again, I suppose, when I put it back. Anyway, you see that there's a constant change of this material. Bring me back to the pollen. I come back to the metals later. The pollen. The pollen is not, of course, it's not an environmental pollution. Pollen is, as Fanny explained it, really important for the honeybee colonies. And for the biodiversity, but also for the pollen for the honeybee as their nutrition. So we took pollen samples every 2 weeks, again with the 9 sampling rounds, and altogether we had over 2,500 samples analyzed in molecularly in Bragança in Portugal. And we did find over 500 genera of plants, and the most abundant are the Trifolium, the Plantago, the Brassica, and the Rubus and Castagne. And you can, and you see it on the right-hand side, you can split up Europe in 3 zones. The northern, the middle, and the south with very typical pollen representatives. We also had here the average on our agriculture, natural and artificial landscapes, and you do see that on agriculture and artificial have higher pollen diversity than nature. We did expect we had more in nature, but no, we don't. Because also the biodiversity in our nature reservations and conservation areas is really diminishing. And I must admit, most beekeepers do live in agriculture areas, and there are not that many beekeepers that have their bees in their natural land use types. For instance, when you go to Sweden, they do have a lot of forest, which is considered to be a natural, but you don't want to keep bees where there's only forest. At least there are not that many. So this is what we had, and I can show you maybe a bit more. No, we go back. This trifolium and plantago, which is really interesting. You see, and I didn't show it because I had not that much time, but you see the same results as we had with colors, with the CSI colors, which was another citizen science project we did some years ago, that main contribution of the pollen diversity is about, for every time, 5 families and genera, which we have a major and about 10 which are less. That has to do with the way that bees collect their food. They are mass samplers, so when there's a lot of food somewhere, all the bees go there, they communicate with dancing, and most of them go and take them this pollen. But they are wise enough to divide it, so we always find more of this pollen genera. We are in Spain, so I thought let's show you something about Spain, and here the results of the heavy metals, and you have these black diamonds, which means that's the average of a country. This, in this study, and you have the open diamonds, which are the European averages, also on our data. And I show you this because when you look at the left side, which is apiary number 16, you see that most metals are below this row of the black and the white diamonds. And there are, most of them are below it. And you see here first the row of the metals, magnesium and iron, etc., which are measured in another dimension as the other ones. Also here, so it's all below, and on the right-hand side you see the results of another apiary here in Spain, which is Spain 13, and there you see that the heavy metals are above the averages in Spain and in Europe. So we could see all the differences. And I did not show here all the spots and the emissions, because then you see really a high increase. And on the right side, there is this pollen where I told you about, also of beekeepers 16 and 13. And I said, and this is a graph with the 9 sampling rounds. It's in time. You go from the left to the right reading it. So the left side are the pollen diversity in April, and on the right side in August. And you see this, the major stuff is made every sampling round by 3 or 4 pollen genera. And they are completely different in every apiary that we had. So in this case, you had this, the blue one, which is apiary 13, which is high in the beginning, and then in summer, and at the end there is no blue anymore, and the same see above. And on the top side, you see the green, and I don't know by head which one it is, but you see that it's beginning in more or less in May, and there's a massive contribution towards the end of the year. So you do see this shift in pollen income. At the end, we don't do it for ourselves. We do it for the environment, we do it for the scientific community, we do it for the European Union. All the results go, of course, they are owner of these results, they go to the European Union. And up till now, we have in this project, we have up to 8 scientific papers and a lot of, I call it articles, in the local papers, but most of all, and which is really important, that we have proven that you can, with citizen scientists, organize a study, and really a pan-European study, which provides the baseline for further studies of the environmental monitoring. And with this, I thank you for your attention, and if there are questions, I'm happy to answer them.